view, sound and cameras. So Tim, you can still unmute and talk and all that good stuff?
I hope so. Can you hear me?
Yes, indeed. Sounds good. And Allison, you're good to go as well?
Testing?
Yes, excellent.
Okay.
Okay, perfect, perfect. All right, so let's go ahead and get going here. Tim, while I'm doing the little introduction here, you should go ahead and feel free to go ahead and start sharing your slides as you like. I'd like to begin by welcoming everybody back again to the SMU Physics Department Speaker Series for Fall 2020. Today is the last in the October series of talks, which was sort of themed around the concept of probing the unknown. And I think we're going to end today, this particular month, on a very nice collider-centric view of how to go beyond what we know and search for things we don't yet know. So in a moment, I'm going to hand things over to Professor Alison Dayana to introduce our speaker, Professor Tim Andeen. But before we get started, as usual, and folks on Zoom will be inoculated against this already, if you want to ask a question and you're connected to the Zoom part of the seminar, just remember to fire up the chat window and type the word speak in the chat window. And then Allison or I will, at the next break in the talk, if it's during the talk, or at the next queuing opportunity during the Q&A at the end, we'll unmute you and call on you to ask your question and have your discussion with the speaker, of course. So of course you can ask questions during the talk, and we'll try to interrupt the next convenient time, probably at the end of a slide. But remember, don't start asking your question until you've been assured by either me or Allison that the mic is in fact ready to be unmuted. And just for everybody in general to keep in mind, this event is being recorded on Zoom, and it's also being simultaneously live streamed on YouTube, and that's a non-interactive stream. One other thing I want to mention today. So our speaker is quite a trooper. He's giving this talk from CERN in Switzerland. So this is a bit of a time difference for him. He's ahead of us this week only, I guess, 6 hours, which I think isn't the worst thing in the world. But that also means we're incurring a small time delay on the interaction. It's sort of 1 to 2 seconds. So don't be surprised if there's a little bit of a lag between waiting for a response and getting a response. So with that in mind, let me now welcome Professor Alison Dayana to introduce today's speaker. So Allison, go ahead.
Hello, I'm happy to introduce to you today Tim Andeen, who is faculty from UT Austin just down the road, though connecting from very far away. So thank you for joining us for what is for you a late evening seminar. Okay, so Tim has been involved in particle physics for quite some time. He did his thesis with D0 on the measurement of the W boson mass with Northwestern University. After that, he was a CERN fellow and then had a postdoc at the Columbia University before he ended up here in Texas in UT Austin. Okay, so Tim, I have worked with a bit on the liquid argon calorimeter, and I am sure looking forward to seeing him talk today on new physics with top quark decays, and also a little bit on the calorimeter as well, I think, right? So everyone, please welcome.
That's right.
Tim Andeen.
All right, thank you all very much for that nice introduction. And I assure you that if there's any lag in my answering questions, it's just the ocean. It's not me having to think about something. But no, I'm thrilled to actually give a talk here, or give a talk remotely to SMU. I think I recognize quite a number of the faces in the audience here, and I just want to say, I know there is a lot of overlap in what we do at UT Austin, what you do at SMU, both in ATLAS and in particle physics and beyond. And I think it's we should take advantage of this our close geographical connection as much as possible. So I'm looking forward to visiting in person at some point. Hopefully, well, when conditions allow. But I'll just jump right in then. So yeah, I'm going to tell you about some new results on from searches for new physics using top quark decays, and from the ATLAS experiment. And so I'll tell you about that. I'll tell you a little bit about some phenomenological work related to this also, and then a look forward into the what comes next in our searches for new physics and how we're going to build our way there. And on that topic, you might notice in the background here, so of course this is a picture of ATLAS. In the background, you see some building blocks, some Legos. So I think both today and when I was much younger physicist, I really make a connection between the building blocks are thinking of the particles that we have as building blocks of the universe. So I'm going to start with the distant past, and of course we know this and we're familiar with this. This is the discovery of the Higgs boson, right? So this is now 8 years ago, all of 8 years ago, right? So it made a lot of news. It was a big deal. It was a big deal. But now those 8 years have passed, and the graduate students that this inspired 8 years ago to go into particle physics are, some of them are already graduated, and it seems like a great deal of time has passed, and people are wondering what comes next. And it's a reasonable question, but I really do believe that we're at the very beginning of our search for new physics and our understanding of the physics that we've discovered, the physics of this Higgs boson. And we have so many, and I hope to convince you further that we have so many open questions and so many new questions to learn about the physics beyond or behind the Higgs boson. And the tool we're going to use to do that is these top quark decays. So we'll use our Lego scientist here, and she'll show us a little bit about what we know. So just a brief overview. So I know this is a seminar, so a lot of us are familiar here with these ideas, but just very quickly to summarize, as my experimental particle physicist view. So obviously very simplified, right, for us experimentalists, but we have our building blocks, and these are the particles of the standard model. So our quarks and our leptons, with our bosons at the center there, our force carrying boson. So those are our building blocks. And we have our instructions. So just as we have instructions for building our firehouse with our Legos, the standard model provides instructions in the form of a Lagrangian density, which if we squeeze it really hard, we can fit it kind of on a coffee mug. But the point is that this is really just a set of instructions. It provides rules, guidelines, and not guidelines, but rules for how often things will happen, what sort of interactions can happen, when they can happen, and how they can happen. So it's a set of rules that tells us, an instruction set that tells us how to assemble our building blocks. And of course, at the center of this is the Higgs boson, and it's rightly placed in the center as the keystone of the standard model, providing a mechanism for providing the mass, or interactions with provide the mass to our fundamental particles, our electrons or our quarks. And then also, more importantly, in some sense, the particle manifestation of this broken electroweak symmetry. And it is this discovery that is actually, the discovery of this Higgs boson is actually, in a real way, raised a lot more questions than it has given us answers, though it has answered this major question of the standard model. So that's what we're going to talk about in the next few minutes here. But now that we've gone over sort of very briefly what we know, now the question of how do we know this is the next one that I want to just briefly review. And as an experimentalist, so how I know is by building detectors. And fortunately, and it's I can occasionally afford to build detectors from more than just Legos. And the detector I use is at the accelerator at the Large Hadron Collider, of course. And so I just used the slide to illustrate, there is a real connection between our work that is done at the university, whether it's UT Austin or SMU or other, and the work that is done at CERN. So even though there's only one CERN, only one facility like this, only one detector, we really do build these detectors in our laboratories at our universities. Bring that material, bring those subdetectors, bring those electronics to the lab here, install them, work together, providing real support in the form of postdocs, in the form of graduate students at CERN, helping to run and operate the detector on a day-to-day basis. And it's not just exporting our expertise to CERN, it's also bringing it back to Texas. And it's bringing it back as these students return to write their thesis and to do their analysis and then publish their papers. So it's a two-way street. It's not just that we export our knowledge, it's that we this knowledge and this effort goes both ways. And I know the same is true not just at UT Austin, but at SMU and many other places. So the aerial view of the Large Hadron Collider, so I won't go over this in too much detail, except to say that the analyses that I'm going to discuss today were collected at 6.5 or 13 TeV center of mass energy at the ATLAS detector in what we call run two of the LHC, which in the end provided 139 inverse femtobarns of data collected or usable data collected by the ATLAS experiment. And of course, the ATLAS detector is, this will be the one picture I show of the ATLAS detector in bulk here. So I often compare it to the size of a blue whale, though in reflection, I do always remember that not everyone's seen a blue whale, including myself, but it's large. But that's not the point to take away. The point to take away is that it is a collection of many subdetectors, each with their own important role to play. And some of them, although subdetectors, are incredibly large detectors. The muon system is, of course, enormous. The calorimetry system, which I work on and some of your colleagues at SMU work on, is also the liquid argon calorimeter system is also an enormous collaboration of a very dense detector at the very least. But it's like this collection of all these subdetectors that allow us to make the measurements that we use to do the analyses that I will be discussing in a few minutes. So before I go on to discuss new physics, I would like to just stop here for a second on this plot of the standard model cross-section measurements that have been made by ATLAS in the last few years. So it's a very big plot with a lot of results on it. So, and I don't mean to go through this in detail, but I do think it is worth going through it quickly, just because it does, I think, set a sense of the scale of both what our theoretical colleagues are doing, and also what we can do and what we are doing at the Large Hadron Collider and with our detector. So the y-axis is really showing you the different processes. So this is measurements of cross sections and compared to theoretical predictions of these cross sections, starting at the top with the most common, which is proton-proton interactions. So in other words, the idea that anything happened, the protons in our detector collided at all, going all the way down in the middle to rare and rarer processes. So going down a little bit, you see the top anti-top production, or single top production in the upper half. In the middle is actually the Higgs boson production, and now we're probing even rarer and rarer processes of the standard model. And on the x-axis, the thing to note there is that it's the actual cross section, and it's a broken scale. So we are actually measuring cross sections all the way from 10 to the -1 or almost 10 to the -1 picobarns, all the way up to 10 to the 11 picobarns. So it's an enormous nearly 12 orders of magnitude range. So this is a testament to both the sensitivity of the detector, but also to the theoretical predictions. So the data points are in the filled circles or squares or triangles, and they're compared to they're shown with the theoretical predictions in the gray bar. So these theoretical predictions and these measurements are across this entire range shown to be in very good agreement. And we can see that even more clearly if we look at the comparison of data over theory, as one does divide data by theory, and one finds that this is all very, very close to 1. This is remarkable. Across 12 orders of magnitude, we see that this remarkable agreement between the standard model predictions and our experimental measurements. So what you might wonder at this point is, you might be a little bit worried that I've sort of shorted the talk by about 40 minutes. With this excellent agreement between the standard model and our measurements, you might be a little bit worried that this is the end, as our Lego thinker here is beginning to get a little concerned about. But you might also guess that I was aware that this is an hour for the talk, so we're going to have a little bit more to say. And so there are, of course, many open questions in the standard model and many open questions that motivate our searches for new physics. So as I like to tell my students, the standard model predicts 4% with extraordinary precision. So we just said this extraordinary precision to these 4%, to 4% of the matter energy budget of the universe. So as our astrophysical colleagues tell us, there's a lot of dark matter out there, a lot of dark energy out there. We've done a great job with 4%. Well, if you do a great job on 4% of my final, you're not going to do so well in the class. So we're really not, so it's an amazing accomplishment where there's a long way to go. We know things like neutrino oscillations and neutrino mass. So where does this neutrino mass come from? We know there's the Higgs boson, but is this the same mechanism, or is there something radically different? How will we know that? And last, of course, things like a potpourri of options, but one of which is a favorite is gravity. What about gravity? Is there a connection between our standard model work and our work with the standard model and understand the standard model, and what comes next? Is there a connection to string theory? Certainly, I don't know. But we don't have that answer. And I think what this is really pointing towards, and what gives us a good way of thinking about this, is that we think about the standard model as an effective theory. And so we no longer approach this as if this is, breaking a final theory that's, a truly fundamental theory that describes the universe. It is an effective theory. It's something that we know is correct to some energy lambda. And above that energy lambda, so to the energy to where we have measured, above this lambda, above this energy scale, the theory is no longer applicable. We don't know. So there are many great examples of this from the past, from particle physics and physics past. And one example is, of course, Fermi's theory of weak interactions. It's a great effective theory at low energies, predicting neutron decay with neutrinos and the discovery of neutrinos. But at higher energies, of course, we know that at the scale, at lambda, the electroweak energy scale, we discovered the true microscopic description is the electroweak theory. So we know that it's actually not protons and neutrons, but it's up and down quarks, W bosons, and W bosons decay into electrons and antineutrinos. So is there a hint of what comes beyond or behind the standard model? And that hint, I would say, is a big one in the Higgs boson. So the Higgs boson is special. It interacts with all massive elementary particles. So whether there are particles we've discovered or potentially particles we haven't discovered. So for example, supersymmetric particles would interact with the Higgs boson and change our measurements of the Higgs boson. They would be potentially observable through these interactions. And it's also the case that the mass of the Higgs boson isn't predicted by the standard model. So we might hope that a model of physics or a description of physics beyond the standard model would provide a description or a prediction for the mass of the Higgs boson. And so I don't know what that new theory would be, but I can tell you something, or I can know something about that. So I can say that above some scale lambda, and I've set it not arbitrarily, but just above the energies that I'm currently probing. So above this energy scale, new physics lies, and I don't know what that new physics is. So I can separate that new physics from the physics I can describe at lower energies. And at lower energies, it must be the standard model physics. So I can, though I can't write down what the new physics is, I can tell you about the standard model contributions to the Higgs boson mass. So again, if I'd like my new theory, my theory of physics beyond the standard model, to include some description of the Higgs boson mass. Now, the standard model contribution to that, I can write down, as I just said. So when it comes, actually, some of the largest contributions, or corrections to the Higgs boson mass, or actually the mass squared, come through diagrams. So top loop diagrams where they interact with the Higgs boson in this diagram here. And as I write down the contribution from below this value lambda, I find that the contribution to the Higgs mass squared goes as 3/8 pi squared times the coupling of the Higgs boson to the top quark, which we can assume to be close to 1, times this lambda squared. So if I want to keep my Higgs mass, my corrections to the Higgs mass close to the Higgs mass, then lambda must be somewhere nearby, somewhere between 1 to 10 TeV. If lambda is enormous, if there is no new physics until I get to, say, the Planck scale, so many orders of magnitude away, then I really don't have a prediction for our theory with a prediction of the Higgs boson mass. Furthermore, there must be, so we know what the Higgs boson mass is, it's 125 GeV. There must be some equal and opposite contribution, some equal and opposite correction from this new physics sector, which a priori has no connection to the standard model of physics, to that almost exactly cancels, almost exactly, but not quite. So this is what we call it seems unnatural. So that's what we call this unnatural prediction or unnatural aspect of our current situation. And it seems hopefully compelling that there should be or could be new physics just near where we are beginning to probe with our measurements today. So what sort of new physics will this look like? There's several options, of course, many options, but the broadly speaking, these models can be classified in two broad categories, and one of them is supersymmetry. So this is where we have a new fermion boson symmetry. The Higgs boson is elementary, and it is also responsible for generating the mass of these new particles, but the mass is protected by a new symmetry. This is an attractive solution, has a dark matter candidate, string compatible, etc. But there are many experimental constraints. So this plot on the bottom here, I'm not going to go in. It's definitely too small to read. But this is a plot of ATLAS SUSY searches and their most recent limits. And the takeaway, the way to understand this is by these blue lines. The further these blue lines stretch across the bottom of this plot to the right-hand side, the greater the constraints on the supersymmetric model under test or the channel under test is the greater that channel is being constrained. And what you can see is they are past this 1 TeV mark in many cases. Now, of course, there are ways around these experimental limits, but it becomes less and less the SUSY that you're familiar with, and more a constrained sort of SUSY. So it's not, it is an attractive solution, but it is certainly becoming very constrained. Another broad category is composite Higgs models. So in this case, the Higgs boson doesn't exist above some new scale where new strong dynamics is taking place. So this is like QCD, but at the TeV scale. So there's a mixing between this composite sector where new physics lives in the elementary sector, and the top quark may play a special role here. So there's a potential for dark matter candidates, and in the context of extra dimensions, it can be useful to think of this as the new physics taking place in the bulk, where the standard model is confined. But in general, the way we would observe this in our detectors is by new resonances, either new bosons like a W prime or Z prime, or colored fermionic resonances like a vector like quark. And so we'll come to searches for these in just a moment. But before we start searching for these, I want to really motivate where we're going to look for these this new physics. So we've talked about the top quark. Theoretically, it makes sense to be thinking about searches for new physics connected with top quarks, but is it a good place to look experimentally? And I think I hope it's convincing that in fact it is. So this is a picture of one of the top quark events or top anti-top events observed in the ATLAS detector from the roughly 275 million top quarks produced. So this is the largest by orders of magnitude data set of top quarks we've collected so far. So that alone makes us an excellent place to start. So this is also, these top quark signatures are also a very characteristic, a very identifiable signature, at least a very identifiable signature in our detector. So we'll pick apart this diagram here, but because this is characteristic of how we identify top quarks in the ATLAS detector more broadly. And what you can see is that this event has an electron and a muon. So this is an event where both tops may have decayed, or both top quark candidates may have decayed into a W boson, which then decayed leptonically. So we have these nice signatures of our of our muons and our electrons. And then we have our jets. So the top decays into a W and a B quark. So we've tagged these B jets, and the B jets are identified as these cones, these yellow cones that you see. And it's the energy in the cone that is actually reconstructed at the detector. And the energy is it's these yellow blocks or these green blocks. And these blocks, the size of the block is proportional to the amount of energy that's been deposited in the detector in that region. So this is reconstructed as a jet and identified as a B jet, also in part because you can see the straight lines emanating from the vertex to that in that jet. And that is the tracks from the B hadronization that is then allows us to identify a displaced vertex that identifies this as a B quark or a potential B quark. So this is how we find top quarks in our detector. And we have an enormous a sample of top quarks or top anti-top events with which to search in. So with that behind us, we can now move on to sort of some of the meat of the talk. So I want to tell you about several new searches, so fresh from the last few months, recently public searches for new physics involving top quarks in the final state. And then I want to tell you a little bit more about some searches for vector-like quarks and ongoing work there, especially involved in the interpretation of those results. So this is the search for dark matter associated with a single top quark. And this is the case where we're looking at models where there's a dark sector. So in this cartoon that you see on the upper right-hand side here, there's a dark sector and it's connected to the standard model sector. And these signals are described, or this physics is described in two Higgs doublet models plus a pseudoscalar. So a pseudoscalar A. So we have our two Higgs doublets, so our little h and big H, and then also our charged Higgs bosons, H plus and H minus. And this comes with this little a, this pseudoscalar, which is this connection to the dark sector. And so you can see in the Feynman diagrams, Feynman diagrams in the middle here. So this A is decaying into this pair of dark matter particles. And this interaction also includes a W minus and a top quark in the event. So we search for detector final states that have one or two leptons, and we identify these as, along with one B jet, a missing transverse energy of at least 250 GeV. So that's this connection to these. That's the connection to these dark matter particles, which of course don't interact with our detector, and then a missing transverse energy with the lepton of at least 30 GeV, and then the dilepton mass of greater than, if there are two leptons, greater than 40 GeV, but excluding the Z mass window if both leptons are the same flavor. So if there's a pair of electrons or a pair of muons. And to go in a little bit deeper, so let's take one example, one channel as an example. So we'll focus on the two lepton selection. So we use a dilepton trigger with an opposite sign plus jets trigger, and then we use transverse and angular quantities to improve the signal sensitivity. And so on the table on the right-hand side, we have the selections that we make. And so that selections include the signal region, so which is labeled SR here for signal region, is what we are finally looking in to do these searches. And the signal region is two opposite sign, exactly two opposite sign leptons that aren't in a Z boson window with jets and with some jets and some B jets. And then we make use of these invariant mass quantities that you see here, or minimums or maximums of invariant mass quantities that you see here on the bottom and then the opening angle. So this is our signal region. But before we look in the signal region, we do these analyses as blind analyses. So before we look at the signal region, we first look at control regions. And these control regions are designed to accentuate certain backgrounds. So the first control region, so the top anti-top control region is the second column in this table. And this is also the first bin of the histogram on the left-hand side. So if you look in the first bin, it corresponds to that table there. And you see, in fact, in the filled colored histograms, which are the background Monte Carlo prediction, you see that the top anti-top background is in fact the largest contribution in that bin. So as we had hoped. So we use these control regions we allow the control regions, or we use these control regions that are fit of the data to the background. And then we check to make sure that this description of the background is accurate using these validation regions labeled VR. So the validation regions are then shown on the right-hand side of these plots. And you see, again, with the data points in black and the filled colored histograms as the Monte Carlo predictions after fitting, you see that we have done a good job of describing the standard model background. Now these control regions and validation regions are designed to be signal poor. So we particularly make sure that these are signal depleted regions. And we do this work before we unblind the analysis. So we don't look in the signal region until we've ensured that the background description is accurate. So once we've done that, of course, so that was one channel. There are 10 signal regions, so 3 channels. So a top plus jet channel with different missing ET requirements. So this is a single lepton channel where we have 4 bins, and we use a machine learning, so boosted decision tree output to help identify the signal. And then we also have 2 channels where we look for a top plus a W boson, where we use 1 or 2 lepton signatures. And in the 1 lepton channel, we have 5 bins binned in missing ET. So from larger to higher, or smaller to larger. And as you can see across this across the range here, the agreement between data and Monte Carlo or the data in the background model is actually very good. And except in the bin at the furthest right-hand side. So you see some deviation from the background prediction there. That's the 2 lepton region. And so that region was actually studied very carefully. But in the end, it turns out that this is consistent with a fluctuation above the standard model background. So not a compelling signal. So in the fact we don't observe an excess, and so we exclude these lower mass hypotheses. And so what we do is we set a statistical combination. We make a statistical combination between the single and 2 lepton channels for the top plus W events. And this is shown, so one of the interpretations is shown on the bottom right-hand side here, where we show the exclusion region in the combination in the purple distribution, the heavy purple line. This is done as a function of the mass of the input parameters of this particular 2 HDM model. So 2 of the input parameters are the mass of the pseudoscalar and the mass of the charged Higgs. So in this case, this is done at a particular value, for example, at tan beta. So there are other parameters that make interpretations like this more interesting. And we'll come to that in a little bit. So another new result, so switching gears, well, not exactly switching gears, but moving on to a different new result. This is searches for top quark resonances with jets. So this is, again, a result from this summer. And here we see we're searching for top anti-top pairs that instead of, as in the standard model, are produced, in some cases in new physics models, they could be produced through a new heavy resonance, which we just label X in the cartoon on the left-hand side. So in this case, what we're looking for is a smoothly falling background. So this red cartoon, the red line in the cartoon in the middle, and a bump on that would be our new signal, a new resonance. So in this case, the red line would be the top anti-top standard model background, similar to for example, the gamma-gamma background in the Higgs boson, Higgs to gamma-gamma channel. So in this analysis, we looked at the all-hadronic decay of these top quarks. So in this case, both of the W bosons were required to decay to a pair of quarks. So this new model, or these new physics models that include this sort of resonance, include a number of models actually, but we searched specifically for our samples or signals of top color assisted technicolor and certain dark matter models. So again, instead of writing a table to tell you what the selection is, I thought I'd show it to you on the event display. So this is, again, one of our events of selecting a top anti-top event. And the mass of this the invariant mass of this top anti-top event is over nearly 5 TeV. This is one of our most massive most massive events that we find in the detector in this case. So we use angular variables, as you can see here. So you can see the top decays are all hadronic. So you see this characteristic energy deposition in our calorimeters. So in the green or the yellow tiles or blocks, and these events are typically back to back. So we use these angular variables. So the opening angle in phi between jet 1 and actually that should be jet 1 and jet 2. And also selection on eta to ensure that these are back-to-back analyses, and also requiring that the jets have a certain large transverse momentum. But in addition, this is the first analysis using a new deep neural network to identify top quark decays into jets. And so this is a technique that's becoming more and more common in particle physics, I think. And it's to really take advantage of and profit from the work that's been done in industry, especially with image recognition and in other areas, to use these neural networks to really squeeze our data and make the best use of it as possible. In this case, you can imagine that we can use these techniques to identify. So in this case, there are these three green clusters in the event in the bottom left, or the top candidate decay in the bottom left-hand side. So these three clusters are characteristic of top decay into a B quark and then a W that decays into two jets of energy also. So in this case, by eye, it's actually it's relatively easy to pick this out and see that this is what has happened. So that's the pattern that we're looking for. And you can imagine that instead of relying on your eye to pick these out, you might gain even greater sensitivity by using neural networks that are specifically designed to be able to tease this information out. And in fact, that's the case that we find. So we use several jet moment related observables, such as substructure, as input into this algorithm. So the substructure, so jet transverse momentum, combined mass of the energy in the jet, and these other jet substructure variables listed here. So it actually results in a large improvement over previous algorithms used by ATLAS, and making the background rejection substantially larger. And I'll show you the quantification of that in a second. And this is especially true at high mass. So the results you see in the plots on the right-hand side here. So again, we're looking for a bump on a smoothly falling background. The backgrounds are entirely data-driven. So we select a control region to determine the background and then do a background fit. And that's shown in the red line here. And then the data points are shown in the black. And if there was a signal, you would see it as a bump in the signal. So Monte Carlo, so samples of a signal from Monte Carlo are shown in, for example, the solid green line, or the dashed blue line at 2 TeV and at 4 TeV. So although there are some deviations from the background prediction, it is in the very high mass region. And again, we find that this is consistent with statistical fluctuations. So we can't yet say, so there are no compelling signals here. So we go ahead and set limits. So, and just these two plots that I'm showing on the left-hand side is the signal region where one B jet or one B tagged subjet is required. And the other side is the two B tag region. So both top candidates have to have a B tag. So it's slightly more stringent requirement. So in this case, we exclude masses. So the exclusion plot is shown on the left-hand side. In this case, we exclude masses up to 3.9 TeV and 4.7 TeV for different decay widths. So whether or not we expect this new resonance to have a width of 1% or 3% respectively. This is substantially larger than the previous result from ATLAS with 36 inverse femtobarn. And you can really see the impact of this new neural network on the plot on the right-hand side. So we show our previous limit on the black line with the triangles, with 36 inverse femtobarns. We take 36 inverse femtobarns of the current data set of the entire 139 inverse femtobarns, and use this current analysis on just that fraction. So making it fair comparison. So the blue line and the black line are fair comparison between two same-sized data sets that shows the improvement there is really just from, or predominantly from, this new neural network. So, and of course, the line that you see on the left-hand side is repeated on the right-hand side in green. So this is hopeful because we are now in an era when we are not going to be doubling our data sets every year or every couple of years even. So it will be much slower going in that regard. And it really behooves us to make more of an effort to improve our analyses beyond just adding data to these. So I'd like to move on now to another class of searches for new physics. And this is,
Tim, sorry,
yes,
just want to
go ahead.
We have a question from Pavel Nadolsky. Let me go find him in the, okay, there we go. So Pavel, you should be able to go ahead and ask your question.
Yeah, yes, hi, Tim. Well, actually, I have a question about this very interesting slide. On the left-hand side, you show the yellow and green bands for the uncertainty. On the right-hand side, you don't show any of this. So then how do we interpret this, the right-hand side?
Sorry. So on the right-hand side, so no, this is just to compare the absolute value of these observed limits. So this is, just let me make sure I'm not making this up. Right. Sorry. So this is the expected limits. Sorry. So these are the expected limits. And this is comparing this with the latest analysis techniques and the previous analysis algorithms. So this is really just to extract or show you the improvements as a result of the different analysis technique or different analysis strategy. So it's not, so I would agree. I mean, I think it is absolutely fair to look at the plot on the right-hand side and, translate the uncertainties to the plot on the left-hand side. And yeah, you can say that this is either, and you can see how close this is to the uncertainties and how significant that is. But, and also that you find the same uncertainties or comparable uncertainties in this the paper that is cited on the top there. So we left those uncertainties off just for clarity of presentation. So looking, yeah,
well,
go ahead.
Are they big? Because again, the neural network can be trained in different ways, and it has some uncertainty of its own.
Yes, of course. So the uncertainty is those uncertainties are taken into account basically through the by varying the uncertainties of the inputs to these neural network or to the neural network. So the inputs are, so if I go back a slide, if I can. Yep. So these inputs, so like the transverse momentum or these mass variables or these substructure variables, so those have uncertainties that we can vary, and they, we study correlations between these as we apply them in the neural network. So by doing that, we can take that uncertainty into account in this final plot on the left-hand side.
Okay.
So a follow-up question on that, Tim, just to help us understand the comparison on the right-hand side. The black and the blue, those are essentially run on exactly the same events. Is that correct? At least it's the same underlying data sample, 36 inverse femtobarns. That's
right. It's the same 36 inverse femtobarns. It's not exactly the same events. There's, it's slightly, there's a few events, a handful of events. I'm not exactly sure how many, but a few that, don't make the new selection or for some reason didn't pass some criteria in the new reprocessing. But it's almost.
Yeah. So then to first order, there's no statistical difference between those two samples. So if the bands on the left are dominated by statistical uncertainties, then those statistical uncertainties don't exist in the comparison of the black and the blue on the right. That's an absolutely fair shift that has nothing to do with the statistical uncertainties because it's run on the same events. Is the statistical uncertainty bigger than the systematic error, or are they comparable, or is the systematic error bigger?
Yeah, thank you. So that's an excellent point and a good follow-up question. So this analysis, the previous analysis, the next analyses are all statistically limited. So the statistical uncertainties are the largest uncertainties in these measurements and these searches. That's correct. So is it like a factor of 2? Offhand, I've forgotten, but I think it's substantially more than a factor of 2. So yeah, what you said was very accurate, and I think I understand Pavel's question about the uncertainties with these neural networks a little better. So thanks.
Okay, thank you.
All right, I'll go forward. So I wanted to tell you, take a little bit of time to tell you about searches for vector-like quarks, which are so vector-like quarks are new heavy quarks that evade the limitations on the traditional standard model or traditional quark extensions to the standard model by being vector-like. So in other words, their left and right-handed components transform identically under the standard model gauge transformation. So they come as partners to standard model quarks with the same charges. So charges like a vector-like top will have the same charge as the standard model top, or a vector-like bottom likewise. or they can have more exotic charges and arranged in singlets or multiplets or various degrees of complexity. So they also they mix with their standard model quark counterparts, and they help regulate the Higgs boson mass. And they are produced through two different mechanisms. So either pair production, which you see on the left-hand side, or single production on the right-hand side, the two Feynman diagrams here. So in the pair production case, you have, it's a QCD process. And in this case, the only free parameter in describing this process, describing the cross-section, is really the mass of the vector-like top in this case. Excuse me. On the right-hand side, in single production, the vector-like top is produced in a single top-like interaction between a W and a B quark, W boson and B quark. And in this case, there is an electroweak coupling that that is necessary to describe the cross section. And you can see that more sort of visually in the plot on the right-hand side here. So in this case, it shows in the dashed line the reference is floated away, so I apologize for that. But the archive reference, but the pair production is shown in the dashed. The pair production cross section as a function of mass is shown in the dashed line, and then for various single production mechanisms with a particular value of this electroweak coupling are shown in the the colored solid lines. And you can see that above a 1 TeV or 1000 GeV, single production starts to take over in terms of cross section from pair production. So that becomes the more interesting place to be searching for these new particles. We also assume that their decay is almost exclusively to the exclusively to third generation quarks. So for example, vector-like top would decay to a Z and a top quark, or a Higgs and a top quark. And this results in many interesting signatures. So we have an extensive program targeting various production decay modes. And just one example of this analysis is shown on the, I'll go through here briefly. So we're searching for Z bosons with top quarks. So in our cartoon here of this decay, our Feynman diagram S cartoon, what we're looking for in the final state is one forward jet and a Z candidate, so a pair of leptons, and potentially a third lepton from the top decay to a W. So either 2 or 3 leptons. And in fact, I'll talk about the 3 lepton channel in detail. So we define 2 sets of channels, either for pair production or single production. And the diagram you see is just for single production. So we use this analysis to do both of these searches. And again, requiring either exactly two or more than 3 or more leptons. Sorry. And again, we define control regions and signal regions, and then eventually unblind the signal region once we've confirmed that the control region is working well. So this is, again, the case for single production with 3 or more leptons. And you can see on the left-hand side, the plot on the left-hand side, this is the number of leptons, the background, and the various signal models, and particularly in green, the single vector-like top production as a function of the number of leptons normalized to unit area. And this gives you a hint that the good way of searching for this sort of new physics is in a 3 or more lepton channel. So again, we use a control region, as you see in the middle here. This is for the 3 lepton channel. This is a diboson control region to make sure we've got the background models well described. And then we finally unblind and look in the signal region. And this was with just 36 inverse femtobarns. And we again find that we don't have the statistical power to identify a signal here. And in fact, the data in the background, or the background model, look to be in fairly good agreement. So using that, as well as other similar searches, we prepared a combination of searches for pair production of vector-like quarks. And we having observed no significant excess. And this pair production combination is shown on the left-hand side. And the pair production this is parameterized as a function of, on the x-axis, the branching ratio of the vector-like top to WB, and on the y-axis, the vector-like top to Z and H and T. Sorry, the zoom window is hovering over the axis label. And as you can see, we're setting limits in the TeV region. So even with only a fraction of the run-to data set. Now, on the right-hand side, you see the result of a single production a limit. So the single production is a little bit more complicated. So we have these additional parameters, additional couplings to account for the coupling of the top vector like top two, potentially the electroweak sector. So this is here shown as a function of, on the x-axis, the coupling to the z, and the y-axis, the coupling to the w. And again, the mass, or the mass limits, are shown, or the limits are shown as a function of mass, again, by the brightness of the color. So the brightest colors showing the mass limit. So there's a challenge in that in the past, we have done these these pair production combinations, but I've said that the single production is becoming the more interesting case. So this is a challenge for the future, and it also is, in some degree, an embarrassment of riches. So we have a number of recent results from CMS and ATLAS hunting for vector-like quarks, and in particular, single production. But we have a host of ways of interpreting these results. And there is not a great a consensus on how this should be done, a best way. So we have the result I just showed you on the bottom left, but also from ATLAS, a very similar analysis showing you a very similar result, but this time as a function of the mass at the top, or vector-like top, and a different type of coupling parameter, sine theta L. Same idea, but a very different way of presenting this information, interpreting this result, which really makes it impossible for me to look at these plots and say by eye if how they're doing or how excluded particular regions are. Similarly, CMS has published very interesting results recently, but choosing an entirely different scheme. So we looked at this and thought we could help move these searches forward by coming up with a way of presenting this information in a unified way that makes sense both from an experimental perspective and a theoretical perspective. So that's something that we've done at a small group of us have done from UT Austin, and then a group in Portugal. We've proposed a unique and generalized framework that allows for model-independent interpretation of results. This provides experimentalists with a way to compare and combine results. And in particular, it gives us a really good sense of, if there is something to find, we'll be more likely to see it. And if there's someplace we aren't looking, we'll know where we're not looking. So that's two really key advantages of approaching a method like this, or developing a method like this. And it also provides a benchmark for theorists to interpret their models and confront this with the data from ATLAS or CMS. And it also has the distinct advantage of parameterizing the results in the quantities I'm actually interested in. So these couplings to the electroweak sector, every model comes up with a slightly different scheme, and that's fine. But as an experimentalist, I can certainly measure, and it makes a degree of sense to me to think of this in terms of, so whatever those couplings are, they will predict a value of the width of this resonance over the mass. And I can take that ratio and parameterize this. So whatever combination of couplings, or however many there are, I can calculate that or model that. And I can then plot this and parameterize this as a function of the branching ratio of the top vector-like top decay to a W would be. So again, branching ratios of the width over the mass, these are things that I can actually measure. So these are the quantities I'm particularly interested in. And the way we did this by making a couple of assumptions. So we looked for, we made the assumption that the vector-like quarks are either top or bottom partners, and that these top or bottom partners are heavy, much heavier than their standard model of counterparts. Then we also made the assumption that the analyses were chirality agnostic, in the sense that I can't tell left-handed or right-handed a vector-like top or bottom apart. And in fact, that's the case with, I think, nearly every analysis that we've done so far, and we in CMS. And so again, you can see whatever coupling you put in, you can always calculate this ratio of the width over the mass. And this is shown just an example on the right-hand side, where you see the narrow width, or 10% width over mass ratio in red, and then a slightly larger description, or larger resonance in green. Now, another feature of these models is they rely on this narrow width approximation. So typically, we are interested in narrow width resonances, but experimentally, it's often interesting to search for wider resonances, and to have that have flexibility in this regard. So we have to make a correction to these narrow width approximation. And we derive this correction from this correction we call P, and for the NWA. So this is on the right-hand side, or the left-hand side of this plot's on the bottom here. And we parameterize that correction as a function of this ratio of the width over the mass in bins of the mass of the vector like top. And then we actually fit that to do a functional fit to that, and use that prediction to come back and make for example, the plots that you saw in the previous slide. So hopefully this provides a useful tool for both experimentalists and theorists in these searches for vector-like tops, and especially as we come up on these full run-2 analyses that will have these results. So with that, I think we've come to the edge of the map in terms of the searches that we're doing. So I'll just finish up relatively quickly here with a question about what we'll be doing in the future. And of course, future accelerators and future detectors, our colleagues at CERN are working on these as we speak at CERN and also around the world, and including an effort to build the high luminosity Large Hadron Collider. But what is it that we want to do with this? And so the motivation, so there's many motivations for this. And I think one of the most interesting to myself is looking at this Higgs boson potential. So the one thing that, you might remember, so for the graduate students in the audience, you might remember from your particle physics class, even as an undergraduate, is this Higgs potential, this very characteristic shape for the Higgs potential. Literally, this is the textbook diagram from Thomson's Modern Particle Physics textbook. So what is fascinating is that the shape of this Higgs potential directly determines the properties of the Higgs boson self-interactions. So as an experimentalist, what I see and what I read is that measuring the Higgs self-coupling allows us to measure this shape. And that's, to me, very remarkable. The idea that by measuring, or potentially, if we can measure this di-Higgs production, we can actually probe and map out that, in my mind, is a seemingly abstract shape, this concept of this Higgs potential. So to do this, we look for pairs of Higgs bosons, and pair production is extraordinarily rare. We need an enormous amount of data and improvements to the detector to do this. So the accelerator will give us enormous amounts of data, will provide the improvements to the detector. So again, now we're looking at in the simulation that you see on the bottom right-hand side here, you see that one of the signals that we can search for is the Higgs decay to BB bar and the second Higgs to gamma gamma. In this case, now we're looking for a small bump on top of a small bump in the detector. So doubly challenging. But how do we do that? So, well, we'll skip through this quickly, but we are accelerating, or we are upgrading the accelerator, and particularly if you noted this green line. So the green line shows the increase in the luminosity. So even though the energy remains roughly the same, the luminosity really does increase dramatically at the HLHC. And to accommodate that and to make the best use of that, we will upgrade the detector. And of course, I'm not going to tell you, it's an entirely separate talk and a longer talk to tell you about all of the upgrades, but I would like to mention the liquid argon calorimeter upgrade. So this is something that both groups at SMU and at UT Austin work on. And so I don't think I'll get too much pushback when I say this is one of the most important subdetectors on the experiment. But the subdetector measures the photon energy of photons and electrons. And so you can see the mass resolution of a pair of photons in the plot on the top. So this is a performance plot. So it describes the performance of this subdetector in terms of measuring the energy or the mass of a pair of photons. And the idealized case is at the HLHC is in red. A more realistic case is the open green circles, and a pessimistic case is the closed green circles. So the truth probably hopefully lies somewhere in between. So this mass resolution, however, directly impacts how well, so if we can improve that directly impacts this mass resolution that we need to better identify and to increase our signal efficiency in identifying this di-Higgs production. So it directly impacts this plot on the bottom. And the way we get there is by optimizing the calorimeter readout. And we do this by detector optimization. And the detector optimization isn't just about making use of the improvements to electronics readout or detector improvements and technology available to us since the original construction of the detector. But there's a really key fact that we know now that we can make use of, and that's we do know the Higgs boson mass. When we built this and designed this originally, we didn't know that. Now we do, and we can make use of that, and we are making use of that fact to design and optimize our detectors. So I don't have time to get into that. I'll just say that at SMU and at UT Austin, we do microelectronics development for HEP. At UT Austin, we collaborate with the EC department to test a novel ADC, which you see here, and our happy graduate students testing away. And it's this work that a real input is the fact that the Higgs boson mass is something that we know now. So I'll just close with this a quick update. So the work is underway. The cavern is open. We're upgrading. So this is the first phase of our upgrades to phase 1. You can see happy graduate students and postdocs working hard in the pit. You can see that occasionally, not recently, but every so often a professor will even get their hands dirty in the control room. And I'll just leave you with this, we're just starting on the path to new discoveries. And we've gone over a couple of those potential or those analyses, several analyses today involving searches with top quarks in the final state. So thank you very much for your attention.
Okay, yeah, thank you very much, Tim. Zoom doesn't make it easy to do applause. I'm going to hit my little applause button here, but I have some canned applause I can give you. It's sort of the cheese whiz of applause.
I love it. That's great.
I don't know what cheese whiz is in French, but I'm sure it's a disgusting sound. So, all right, we have a question from one of our graduate students, actually. Sully, let me find you. Sorry, Sully, it's a long list of people today. Okay, you should be able to unmute now, Sully. Go for it.
Hey, hello, everyone. Thank you for giving that talk. But I'd like to ask a question about, I know you're talking about statistical differences and then using neural networks as well. In my undergrad, I worked with Dr. Farbin, or Dr. Amir Farbin at UTA, and he had used simulated data from the Dark Machines project, and I was interested and he was using that to create anomaly detectors with neural networks to identify exotic processes in the Large Hadron Collider. I was wondering about, since we have statistical differences with real data, what could be the problems that you could run into by doing anomaly detection on simulated data, because that adds a whole nother layer of how well did you simulate your data?
Well, that's an interesting question. Thank you. So yeah, so there's a lot of work being done. I'm somewhat familiar with the work at UTA, but not that familiar, but also at a number of other places using neural networks to improve improve the performance. And it as you can see in the analysis that I showed, this top residence search, it does work. So it's a great idea. But I think, so you brought up, so especially with anomaly detection. So what about an anomaly detection when you do see anomalies in your data? And that's a good question, but I would just draw your eye towards, let's see how far back this will go, because it's just gonna keep going because I pressed the button a lot. All right, so let's come back to, for examples, sorry about flipping through here, but this one here. So on the right-hand side here, on the far right histogram, you see that in fact, in this signal region, there's a disagreement. And I don't remember if I put in the backup if exactly what the p-value is for that. And so we looked at this carefully. And so these anomalies do exist, but it's not really anomalous. So if you take into account the fact that you're looking at many different signal regions, you're looking at not just in this analysis, but in many others. If you, the look elsewhere effect in all of these cases, when you do that, you realize that what looks like an anomaly, at least at this level, is just statistical. So if you're training your neural network correctly, and I'm certainly not an expert on that, but if you're doing that correctly, when you're using Monte Carlo to do this, you should see anomalies like this. So statistics is real. You get, if you have 6 million simulated data sets, you should get 5 sigma fluctuations, which would be much larger than this. So I wouldn't say that that's a reason to avoid those sorts of machine learning programs to try to squeeze out a little more from the data. Although my personal taste in analysis is definitely not in that direction. So.
Okay, and I'd just like to add that the anomaly detection was used to, like we did, where you train on background data to find events that were interesting. Okay, well, thank you for answering that question. I was very interested to see the effects of simulated data or not. Thank you.
Thank you.
Okay, yeah, thanks, Sully. And next up we have Roheen. All right, Roheen, you should be able to unmute now.
Hi, thanks. Hi, Tim. Talking to you after a long time.
Hi, how are you?
Good. So I had a question regarding this VLQ search. So not regarding the search, but particularly the framework that you developed. Now that you have a framework which you can use to check the studies that both ATLAS and CMS does. But do you also have plans to take it further, like make a statistical combination of both ATLAS and CMS? Now that with both the experiments, you get more data and you can probably put a more stringent limit.
Well, thank you, Rowan. So I promise that I didn't ask you to ask that question, despite the fact that we've worked together before. No, that's a great question. That is, in fact, what we're working on next. So, of course, the next step is to use this in combinations, and that's something that we're doing internally within ATLAS now. So I'm not supposed to say, but of course, you can easily guess that's one of the big pushes as we finish the analyses of the full run-through data set, and particularly in searches for single vector like quark production is going to be producing the combination. So both within ATLAS and then hopefully more broadly, using the CMS data as well.
Roheen, did you want to make any follow-up comments on that? You can unmute yourself again.
Oh,
Sorry.
yeah.
Yeah, once you mute yourself, you shut yourself out of the queue. So.
Yeah, that's satisfactory. So I just want to say that this is recorded, so whatever you say is out there. Thanks.
Yeah, and actually following up on that question. So the framework itself is fascinating, and obviously I have some reading to do this weekend to actually understand this a little bit better. But how generalizable is this kind of combination framework? In other words, is it tied in any detailed or specific way to vector like quarks, or could it be adapted to other curious states that you might be searching for that don't have a happy home in a well-defined theory?
So it is. So there are aspects of this, of course, that are very much tied to vector like quarks, but it's also the case that so we have here in this some thought. So yeah, in some sense, comparing different models like this that are are potentially describing, in the case of vector like quarks, they describe the same physics, but in other cases where you have closely related models that are describing maybe similarly or the same sort of final state or the same sort of new resonance, where they're the models and the physics behind that, or the motivation for these models may be different. It still often comes down to, a way couplings are defined, and if again, it depends on the certain assumptions that you can make or want to make, as you go through this. So in this case, we made particular assumptions about the vector like quarks are much more massive than the standard model partners. So in some cases, maybe there are certainly examples of models where that's not the case. You want them to be close, or you want one of the new particles to be close to the standard model partner. So that these assumptions don't necessarily translate. But yeah, the general idea, I think, we've thought about it. We don't have a specific use case or implementation in mind. We're pretty busy as it is, but I do think that it could be useful in other areas. I just haven't gotten into that yet.
And I would encourage you, if anybody has a question, go ahead and type speak in the chat window. While we're waiting for that, though, another follow-up question on this, and maybe this is something I should have started with, Tim, but my apologies if I missed this in your slides, but can you just briefly, what's the motivation for looking for a vector-like quark state? What's the original sort of theoretical idea that gave birth to this whole, I mean, there's a broad range of searches now at this kind of collider, CMS and ATLAS for these states. What was the original physics motivation for these? Why are they still so interesting?
Yeah, that's a great question. So the original motivation is, as we've discovered after the discovery of the Higgs boson, let me start before that. So it's natural, well, maybe not natural, that's a loaded word, but we can certainly imagine why stop with 4 generations. So natural extensions to the standard model, you might say, well, what if there's a new up-like quark or a new down-like quark? And so this was something that was explored and investigated for quite some time, and since the early 80s, I think. And then additionally, just as also at that time, as people started to think about supersymmetry, but an alternative to supersymmetry, and really one of the only, in terms of the big picture, one of the few, other ideas we've had, right, is that, well, okay, if it's not supersymmetry, well, there could be some new strong dynamics, something like QCD at the TeV scale or somewhere beyond, and that's difficult to calculate, but that's another option. So that's really where this comes from. But the particular motivation behind vector-like quark searches right now is because we discovered the Higgs boson, and as I was saying, higher mass, so a real standard model like 4th generation particles would interact with the Higgs boson. That's sort of what makes them standard model like. And so we know from measurements of we knew very quickly from measurements of the Higgs boson cross section that this wasn't possible. We would have seen signs for that already. So if you want to add a new quark, it has to have one of the, I don't want to say the only way, but certainly one of the ways, and perhaps one of the only ways, is to do it by making them these vector-like quarks.
Okay. Yeah, I think it's, I personally get to hear about these infrequently. I mean, Rohin has talked about them. I think Allison has talked about them before, but I'm not sure that it's come up in a seminar recently in our department. So I thought it would be useful to maybe get some of the history of this as well.
Yeah.
I see, Pavel, you have a comment as well. Let me unmute you. Okay, go for it, Pavel.
I actually was curious because, as you say, they are spin 1/2 particles, so they are not very vector-like quarks, right? So I think there is a little bit of confusion about what exactly we mean by them. But I could imagine that such particles can arise in models of grand unification, and so they create some additional multiplets that are very heavy to be seen at low energies, but they can start being important when we move on to high energy, where God theories may be important.
So these wind up kind of being a natural consequence of expanding your group theory, or expanding the group that governs your theory.
Mm-hmm.
Interesting. Okay, great.
Thanks,
Tim,
Pavel.
yeah, I see a question from Tim Hobbs. Let me get to the button here. Okay, Tim, go for it.
Yeah, Tim, thanks for this very nice talk. I had sort of a general comment and or question. It's very interesting what you show searching for these consequences of very specific models, BSM models. Presumably there's a mapping, many of these, to a more generalized framework, like the standard model effective field theory or something in this sort of way. Can you comment on that? I mean, I imagine these TT bar and other measurements you discuss place general constraints on various BSM operators that might go beyond just the specific scenarios you're talking about.
Yeah, great question. So that is correct. I don't have a this result here doesn't do that interpretation as in with these DFT operators, but you are absolutely right. It does have an impact, and it is something that you should. Well, it's certainly something that we're interested in on ATLAS, and it's something that you should look for future results in this area, I think. So yeah, I'd say I don't have anything concrete to say on that at this point.
And just quickly for the students in the audience, can you just briefly explain what does it mean to try to like constrain a effective field theory? What is the effective part of the effective field theory, and what are you constraining when you apply these ideas?
So so now you're getting a little beyond my area of expertise, but there are, well, I should probably just admit that, sort of as an experimentalist, the way I approach this, so there are models that extend the standard model in a more generic way, where you just write down whatever operators so possible to write down. So any sort of new interaction, there are only certain number that are possible to write down, and so so we sort of take an agnostic approach. So whether or not these interactions are part of some some complete higher energy theory or not, we can write them down. And so now you can go and search for those, and you sort of divorced yourself from what is the theoretical motivation at these higher energies that you don't care what that motivation is. All you care is that this interaction could happen and you could search for it. And so that's so the program would be to just constrain those types of interactions with searches like this. So I certainly would invite anyone in the audience who might know substantially more about these effective field theories than I do to make any corrections that are necessary.
Well said, Tim. Yeah. Yeah, I mean, my recollection was basically add terms to your Lagrangian that are allowed and are normalizable, and then see which ones would predict the phenomena you're looking for. Yeah, Pavel's got a good comment in the chat here. Yeah, it's like the multipole extension for the full potential electrodynamics. Yeah, very good. That's a nice analogy, actually. That works well, given the backgrounds, I suspect, of most of the folks in our audience now. So, yeah.
Thank you, Pavel.
Yeah. All right, I don't see any more questions. I think this has been a very lively Q&A actually already. So thank you very much, Tim. I know it's not as late as usual as it would be for you because of the time difference closing a little bit. It's still pretty late, and we should probably let you get some rest. So thanks, everybody. Thanks to Tim.
All right.
And thanks, Allison, for recommending Tim as a, as a candidate for this event. And we'll wish everybody a good evening and take care, okay? Bye-bye, everyone.
All right. Thank you. Yep.
Thanks for coming, Tim.
Yeah, no, thank you very much. Bye-bye.